So this is a summary of how you'll conduct the Freefall lab, by which we're going to measure the acceleration due to gravity g. So the parts that we're going to need are this clamp, you can see is connected to a wire, the landing pad, contact pad that goes with it, a steel ball, and the smart timer. And the basic operation that you're going to have is you're going to have the ball clamped inside that clamp, and then you'll set the timer to go, and let it go, and then it hits the landing pad and stops the timer. So now we'll see how to actually do that. So the timer has a switch on the side, and we want the stopwatch function. So we're going to press the red button once to get down to this row, and the blue button 5 times to get to the stopwatch. So in order to make the measurement go, there we go. And so the idea is that you push the piston into place, and then tighten the screw. There we go. And then it'll hold it in place while you press the start button. When you press the start button, you should see a little asterisk there. That means that it's going to start the timer when the ball is no longer making contact, and it's going to stop the timer when the ball hits the contact pad. Like that. The number you get ought to be broadly in the range of half a second. If you get a super short time, like 0.05 seconds, then the measurement has gone awry and you'll need to do a new measurement. So you are going to collect this time data for a variety of heights. You will measure the height from the top of the contact pad to the bottom of where the ball is in the clamp. And then you will create a table of the height and the time it takes to fall, and then you'll use that data in order to calculate g. I'll explain that in a little bit. When you look at your Prelab, you're going to see 2 components. One is using the general kinematic expression that we know from class in order to derive an equation that's specific to the scenario of a ball being dropped from rest. And the second part is to write out a procedure for how you will actually make those measurements. Now, most of that procedure I showed you in the first part of the video, but we will look at some of the rest of it, which is how you're actually going to use the data. But first, let me give you a hint about what we're going to be doing for this component where you're solving a kinematic equation in order to get a function that relates h and t so h is equal to something 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 t something something something. Right, so this is the type of equation we're aiming for. Now, we know a lot of things at the beginning of this problem, even though not all of them are necessarily written out. So our normal kinematic variables that we either know or don't know are summarized in this table here. And I'm going to give you some hints for these. So first of all, anything that is 0, you want to identify. So if the object is, let's just make a little picture here. So we've got the ball starting from a height h. So we know this height is h on our axis of y. And we know that the ball is going to be ending on the table, but at the bottom. So this is representing our axis here. And another feature is that when you're dropping an object, its initial velocity is the same as the velocity of the thing that let go of it. So if it's stationary when it lets go, that tells you that the initial velocity is 0. So in that, I've given you the information basically for these 3 pieces of information. Acceleration, I talk about here, and then we don't immediately know time, but we're going to say that that is a known because it's something we're going to measure. So in the end, your equation should involve a bunch of letters. We have no numerical values at this point. And it'll be an equation that involves h, and g is going to be in there somewhere, and then t is going to be in there somewhere. And these might be raised to power, but that's generally what the function is going to look like. For the next part, I have the video that you saw of the setup. And so your procedure will mostly be writing about how you're going to do it based on what you saw in the video. In terms of the number of trials and values to take, basically a good standard is to have 5 to 7 different heights, and then at least 3 trials for each one. So the number of variables values is 5 to 7 and at least 3 trials. Now, this is the hardest part to get exactly right. How are we going to analyze the result? Well, I've got some simulated data here where I've taken, in this case, 6 different heights and 3 different times, trials that is. And so the first thing you're going to do is just take the average of those. And you can see the data here is in Google Sheets. So you do average of those 3, and then it'll fill in. And once we've got those, we don't really need to worry in terms of discussing this data. We don't need to really see it anymore. Where's hide? There we go. So these are the columns we want to plot. However, even though height was our independent variable that we did in the lab, in physics, we don't always put the independent variable on the horizontal axis. We do whatever is most convenient for the thing that we want to get out of it. So we are going to actually copy and paste the height on this side. And this is just a trick in Google Drawings to get it to graph easily. And then we're going to insert a chart. And we want to check first that it's a scatter graph. So there are dots that aren't connected by lines. We have height on the vertical axis. We have t average on the horizontal axis, which is what we want at the moment. We could do a better title than this, like calculating free fall acceleration, something like that. But we need to do a fit to actually get the information out of this. Now, what I'm going to show you the first time is the right idea, but not the right answer. So if you go to series, you can click on trend line. This is going to do a line of best fit. We want to label it with the equation, and we want to show the r squared. Now, this looks pretty good. This is not correct. This slope and y-intercept are not going to give you anything that you can use to calculate g. You can go for a different type of fit. So for example, this polynomial. which gives you, in this case, the same r squared. But this also is not going to give you anything that you can use in uh, in the calculations. So we're going to linearize this. Now, when you get this equation, I'll spoil a little bit of it here. It's going to have a something that I'm just going to call C, that's some collection of values there, t squared. So I want to make this a linear graph. So at the moment, I'm plotting y, and for so y is equal to h, right? And I'm using for the x value, I'm just putting in t, right? So if we plug in these up here, then you can see that the type of graph that I have right now is really a parabola. It doesn't look like a parabola just because of the data we actually have to use. So in order to make this fit the type of equation that we know it really has to have, we have to go back at this equation and think, what variable can I choose so that I get an equation that looks like a line, which is to say y is equal to mx plus b. Right? So if we compare this equation to this equation, we know this is equal to h, so the rest of this needs to be c times t squared. So if I can replace x with our variable of t squared, then this equation does become y is equal to some constant times x. And the plus b is 0, at least we hope it is. So to linearize this, instead of the horizontal axis of my graph being t, I need it to be t squared. And so the way we would do this in Google Sheets, I'm going to get rid of this for a moment. I'm going to say t squared, and the units are seconds squared. So I'm just going to square each of these in autofill. Now I'm going to once again copy my height. I'm just going to go ahead and reselect these to insert my chart. And you can see the actual graph doesn't look very different. And I think with the specific semi-random numbers I have, it's not going to be very convincing. My r-squared is actually a little bit lower. But I will assert, and you'll see when you do this with your own data, that this slope is actually relevant to the calculation of getting g. And you will hopefully see what I mean by that relevance when you finish solving this equation, figuring out exactly what goes in front of that.